imagine the curve y equaling f of x. The area bounded by the x-axis, the line x equals a, the line x equals b, and the curve can be found by evaluating this definite integral. I've got a b and an a here. These are referred to as the terminals, so it fits above the integrand and below it. I have my rule that describes the curve, so f of x, and I'm working out with respect to x. Remember that the antiderivative of f of x, where f is in lowercase, is equal to capital F of x. So we get this rule, we work out its antiderivative, and then we have the terminals b and a, so the right-hand side and the left-hand side. To evaluate this line here, we simply substitute b into the antiderivative of this, and we subtract from it the substitution of a into the antiderivative of the curve. It makes it a lot clearer when we look at our first example. A, we've got our rule that would describe the curve. We've got the terminals 3 and 2. So to begin with, I write down what the actual question is asking me. Next line, the terminals 3 and 2 go to the right-hand side of square brackets. And inside the square brackets, I've got the antiderivative of this. So 3x squared is going to become 3x cubed on 3. 4x is going to become 4x squared on 2. And negative 1 is going to become negative x. Please note that when you're evaluating definite integrals, you don't need to include the c, the constant, the unknown constant at all. Okay, so just tidying up this expression. I've still got the terminals 3 and 2, but they are at the end of the square brackets. And to evaluate this, I substitute 3 into the rule, and I subtract from it the substitution of 2 into the rule. So I end up with the first bracket, second bracket, and then that simplifies to 42 minus 14, and eventually I get an answer of 28. That tells me that the area underneath the curve is equal to 28 units squared. That's what I've just worked out. Going back and taking a look at the properties of definite integrals. I'll refer to this diagram with it. If you've got the terminals a to a, so they're the same, if you're looking at the area underneath the curve and bounded by x equaling a and x equaling a, that area is going to equal 0. So that makes sense. Can you imagine that if we had that line being brought across so it's directly on top of this line, the area is going to be 0. So that's a sensible idea. We can also break up. So if we're looking at x being between a and b, if there's some point in the middle of that, so let's call it c, then what we can do is go from a to c and then add that from c to b. So this is where c would be in between a and b. So what I'm saying here is that if we had this particular graph, if there was a point in the middle between a and b, let's call it here where my cursor is, then what I can do is work out the area of the left-hand side and then add it to the area of the right-hand side. And that's shown in that kind of format. Again, you've seen this before. If there is a constant, and it's k in this case, of a rule, you can take out the k and put it in the front of the integrand. Also, if we're taking the antiderivative of an expression with more than one term, then you can break each part up. And what's a little bit different for us is this idea. If we have the antiderivative of f of x with respect to x through the terminals b and a, b being at the top and a being at the bottom, then that's going to be exactly equal to the negative of the flipping of those terminals. Let's now take a look at b. So we're looking at evaluating the definite integral of 4 lots of 2x plus 1 to the power of negative 3, where x is from 1 through to 4. So straight away I can take out the 4 and put that in front of the integrand. I'm now going to work out the antiderivative of this expression. So remember the technique here when you've got a linear factor raised to a power. It's going to be 1 over the coefficient of the x, so that's the 2. We lift the power up by 1, so negative 3 is going to become negative 2. That's where the negative 2 comes in. I have my linear factor raised to the new power. And of course what I need to do is put that into square brackets and put in my terminals 4 and 1. Simplifying a little bit here, I have negative 1/4 times the linear factor to the power of negative 2. I can take out that negative 1/4. So now you can imagine that I've got 4 multiplied by negative 1/4. That's going to equal negative 1, so that's why I have a negative here. And now what we can do is substitute the 4 into the rule. That's this here. And subtract from it the substitution of 1 into the rule. And that's that bracket there. Of course, 2 times 4 is 8 plus 1. I get 9 to the power of negative 2. And I get 3 to the power of negative 2. And all of that is negative. So if I multiply that negative through, then I've got negative lots of 9 to the power of negative 2. And negative times negative gives us a positive here. Positive amount of 3 to the power of negative 2. So I end up with negative 1 on 9 squared plus 1 over 3 squared. So of course it's negative 1 on 81 plus 1/9. And then if you express them both over 81, you can see we come up with 8 on 81. In methods, whatever we can do by hand, we can also do with our CAS calculator. So let's just look at A. We understand that if we evaluate this definite integral, we end up with 28. So let's see that on our CAS. I start off with the calculator setting, so menu, calculus, and this time I want integral. You can see I do have terminals, so we're going to put in those values of the terminals. So at the top there I've got 3, and at the bottom I've got 2. The rule is 3x squared plus 4x, take away 1, oops, and I'm doing that with respect to x. I'm going to put an x in here. And all I need to do is hit enter, and you'll see that we get a 28. And there's my 28, meaning 28 units squared.